Okay, good afternoon. We'll continue with our discussion of diode circuits, but a little bit of history before we begin. Today is November 7th. November 7th, if you all, most people don't realize it, is the birthday of Marie Curie. And Marie Curie is, of course, a name that we come across in history books while we are in school. But I find this bit of history very fascinating and interesting. I always like to bring it up. She was the first woman to actually win the Nobel Prize, and she is one of only four people who have won more than one. There's only four people in the entire history to have won two Nobel Prizes, and only three who have won for the scientific research. She is the first and only woman so far to win two. Okay, she's the only woman. She's the first woman to win a Nobel Prize. She's the only one to have won two, and more incredibly, she's won it in two different fields. The first one she shared with her husband and another French physicist in physics. So she won the first prize in physics, and then a few years later, she shared the second one in chemistry. Okay, the other three people are Linus Pauling. He won the first one for, I think, his work in I want to say physics, and the second one for a Peace Prize for leading efforts against nuclear testing. And so that's he won two. Then John Bardeen. Have you heard that name before? From me, you have not heard me talk about it. Maybe. John Bardeen, Walter Brattain, and William Shockley are the three people who are credited with the invention of the transistor, the first solid-state device. So the diodes, the transistors, everything comes from there. And so they won the Nobel Peace Prize in physics based on their invention of the transistor. And John Bardeen, of the three, the three had a falling out. They went their own separate ways. John Bardeen went on to become a professor at, I want to say UIUC. It's either Illinois or Chicago. I can't remember which one. And then he was conducting experiments in superconductivity. So he won a second one for that work a few years later. And then the other one, the last one, is Sanger, Frederick Sanger, I believe. He did his work in the field of genomics, so DNA, genome sequencing. And his work, incredibly, the two prizes he won. The first one was in 1958. The second one was like decades later in 1980. So just to think about high achievers, it's like such a long span, pretty much his entire career, and did some incredible work. So these are the only four people to win it twice. More interesting facts about the Curie family. Marie Curie was Maria from Poland. She moved to France to do research work in physics or whatever, and then ended up meeting Pierre Curie, ended up marrying him. And so they are the first husband and wife team to win, Nobel Prize. You know which one was the second one? It was her daughter and son-in-law. They won the Nobel Peace Prize in chemistry in 1935. That was a few years after physics. So Marie Curie shared the first one with her husband and another physicist, so three people. And then the second one in chemistry was shared with her daughter and her son-in-law. And to make it even more intimidating, her second daughter, younger daughter, so her younger son-in-law also won a Nobel Prize. It was a Nobel Peace Prize for, I can't remember, it was like 1965 or something. So Marie Curie, her husband, her daughter, her first son-in-law, and her second son-in-law. I would hate to be the younger daughter, right? A family of high achievers where everyone has won a Nobel Prize. And I'm like, so yeah, the first husband and wife team and the second husband and wife team from the same family. All right, with that little bit of history, let's get to our discussion. Diodes, let's see, which one am I looking at? Believe this is where we stopped, right? The next slide I had assigned as student practice, and so that's what we're going to cover today. Actually, maybe for a section I may not have assigned this. Anyway, it doesn't matter. This is what we're going to cover today, right? So for this circuit, I think I might have mentioned that we need to find the Thevenin equivalent circuit, right? It's the exact same circuit as the previous one. The only difference is that there's an extra resistor. There's an extra resistor in there. And so if there's an extra resistor, we need to find the Thevenin equivalent circuit as seen by the diodes. So this extra resistor causes a voltage drop across itself, and because it causes a voltage drop, we need to separate it out and convert it into its Thevenin equivalent. Okay, convert it into its Thevenin equivalent. All right. And I'm gonna take a little bit of a shortcut. And paste this here. Okay. So we have two resistors R, right? The previous circuit only had one resistor. Now we have a resistor in parallel. Okay. So the resistor R right here is in series with this power supply. Hence, it is known as a series current limiting resistor, right? And then the other resistor is in parallel with the rest of the circuitry. So we have the same two diodes, and we have a 5-volt voltage source in series with one of those diodes, right? So we need to convert it between these two terminals. And so I show that with the split of these dotted lines, right? Some of the voltage goes down that parallel resistor, so we need to find VTH and we need to find RTH. Where have you seen the circuit before? This was in voltage dividers. Voltage dividers. This is a voltage divider circuit. That's all it is. Okay. Some voltage drops across the series resistor. Some voltage drops across the parallel one. In this case, because they are both equal in value, they both will have half the voltage. Okay. And so the voltage that is applied to the diodes is now half of V in. If you all recall the example that we used in voltage dividers, more specifically the oscilloscope probes, we have a 10:1 ratio at the front, at the back end of the oscilloscope probe. And so the series resistor in there is 10 times the value of the parallel resistor. So the larger the resistance, the more voltage it drops across itself. So in an oscilloscope probe, if we connect the oscilloscope probe to, let's say, 100-volt supply, right? 90% of that will drop across the series resistor, and only 10% will be available across the parallel one, right? So if you apply 100 volts, 90 volts is dropped across the series, 10 volts across the parallel. So the oscilloscope is only actually measuring 10 volts. But when we change the settings on the front panel of the oscilloscope, we tell it, okay, whatever you measure, multiply it by 10. And so then it gives us the correct output. It says, okay, at the probe tip, it's 100 volts. At the input to the oscilloscope, it's 10 volts. Internally, I'm going to multiply it by 10. And so on the screen, I see 100 volts. That's exactly the same operating principle that we have here. Okay, no different. Does that make sense to everyone? Let's take a pause. Let me know if you have any questions. Questions? Okay. So the RTH here is straightforward. It's because two resistors are exactly the same. So R in parallel R over 2, so 0.5 R. Exactly the same value. Okay. And VTH is also V in by 2. So 0.5 V in. And we're simply dividing it to half. By changing the ratio of these resistors, we can have any value of voltage going in. If you want it to be a really high voltage circuit, high voltage measurement device, right? We can increase the series resistance value to any value, to any ratio we want. And for that, I would refer you back to that slides on the voltage divider network. Okay. So if you apply V in as 10 volts, the diodes are only receiving 5 volts, half. So if we go to our previous circuit, what did we see? 5.7 and minus 0.7. That was our operating range. So if that goes divided into half, but we have a 5-volt source, so now our range has increased. V in can go to 11.4. And so when V in is less than 11.4, diode will be off. And for the second consideration, V in must be less than 1.4 volts. Okay. So you apply 1.4 volts at the input, half. 0.7 is dropped across series resistor, 0.7 is dropped across parallel, and 0.7 is the only one going to the diode. So minus 1.4 volts. All right. Okay. And then I want to talk about this circuit. This is one of the most important circuits and most important application for a diode. This is known as the diode rectifier circuit. To be more accurate, this is a half wave rectifier. The rectifier circuit converts AC to DC. Any device that we plug into our power outlets requires DC, right? So AC to DC conversion. So whether it's your laptop or mobile phone or your tablet or this monitor, projector, computers, lab equipment, all of those have a power supply inside them. And the front end of every power supply is a diode rectifier circuit. That's the absolute first component. Okay. So one of the most important applications of a diode. All right, so let's analyze this circuit using ideal diode analysis first, and then we'll talk about CVD model, right? So if it's ideal diode analysis, all we need to realize is whether the anode is higher than the cathode or if anode is lower than the cathode. That's all we need to know. So a sine wave like this, which goes positive, negative, is applied to our input, right, to the diode. In the positive cycle, this is 0. Positive means it's above 0. So this is the positive half cycle. The circuit can be modeled like this. This causes the diode to be on because all values are positive, right? And if the diode is on, what is my V out? Any guesses? What is V out? V out is equal to V in. So it doesn't matter what shape the positive cycle takes. It could be triangular, rectangular, arbitrary, noise doesn't really matter. As long as it's a positive value, the anode is going to be higher than the cathode, so it's always on. And output will be the exact replica of the input. And you can guess where this is going, right? In the negative half cycle, it flips, reverses, and so everything is lower than 0. And if it's lower than 0, then the diode is always off. And if it's off, I'm not receiving anything at the output. Open circuit. Okay, that's what it is. Make sense? Okay, that was the quick and easy analysis with an ideal diode. Now we simply swap out the ideal diode model with a CVD model. CVD model, the only difference is 0.7 volts required to conduct. And so CVD model in a CVD model, of course, reverse bias, there is no difference. Reverse bias, it's going to be off, no change, right? No change. And so the only thing we're concerned is the positive half cycle. In the positive half cycle, in the positive half cycle, the diode is modeled as a constant voltage source of 0.7 volts. Okay, 0.7 volts. So my V out should be a replica of V in, but at every stage, 0.7 volts would be subtracted in order to turn the diode on. Okay. Does that make sense to everyone? Questions? The equations for determining output. Oh, yes, yes. Yeah, it's just KVL. That is correct. Question being asked is how would we obtain V out, or how did I obtain that equation? The answer is yes, KVL. V out is equal to V in minus 0.7. So if we now plot the output waveform, this is what it would look like, right? Let's say, I'm going to draw a very thin line, but let's try this. And this is exaggerated, okay? Let's say this is 0.7 volts, right? So until V in is above 0.7, output's not going to work. It's going, I mean, sorry, the diode's not going to work. It's going to remain off. So my output is 0. So below this level, output is going to be 0. So if I mark, let's say here, and I'm going to exaggerate this a little bit, okay? Sinusoidal waveform is not perfect either. So between these points, the input is below 0.7, diode is off. That means my output V out is 0, right there. Why is it? So here, V out is equal to 0, V out is equal to 0, V out is equal to 0, right? Between those points. And everywhere else, diode turns on, but what is my V out? It is the exact replica of V in minus 0.7. So every point, if I was to break this up, every single point, output would be 0.7 volts less. That's all. And so if I was to do that, I can get, so this would be kind of a straight line here, not there, sorry. All the way up to here. Then it reaches that point. This is not going to be very clarifying. Eh, yeah, it's not consistent, but anyway, hopefully you'll understand the main point, right? There's a difference of 0.7 along the way. Eh, yeah. Okay. There's a gap. I mean, it's not consistent, but there's a gap of 0.7 between V in and V out. That's the point. Right? And when when V in falls below 0.7, output goes completely 0. .7 volts. And this is my V out. The entire waveform V out. Okay. All right. Now, let me ask you this. We've seen two different diode circuits, right? What is the difference between these two circuits? Take a few seconds, but anyone? Does it take more voltage? That's a good guess, but no. Let me ask you this. If you had 10K and 1K like this, and you had 1K and 10K like this, what's the difference between these two circuits? Well, but I mean, the 10K, whatever voltage drop is on the left for 10K is going to be the voltage drop on the right for the 10K. Any difference? Absolutely none. So whether it's a diode or LED or any other component, the series circuit, there's absolutely no difference between those two circuits. They're exactly the same. So these two circuits are exactly the same. There's absolutely no difference. The difference is in the location of the output. Where are we taking the output? Okay. So again, question I was asking was, is there any difference? The answer is no. In the first circuit, we were taking the output across the diode. Sorry, no. That was, yeah. This is this circuit, right? Diode, V in, and then rectifier output across the resistor. And then the first circuit that we looked at, or right here, this one. Resistor in series and output is taken across the diode, right? And so that is this circuit. Output is taken across the diode. Pointing out that there is absolutely no difference between the two circuits, except we are drawing the position the other way. And we are, even if physical connection is made the other way, still the exact same circuit. You can try this in the lab. Very easy experiment to do. Take a diode, take a resistor, apply a sinusoidal waveform V into it, measure V out across the diode and the resistor for both circuits, and see and compare the four waveforms and see what you obtain. Yes. Absolutely. Yes. Question being asked is, can we rearrange in a series circuit? Can we rearrange the components in any order we want? The answer is yes. Yep. The answer is yes. Because here's the thing. If we were Ant-Man, we could borrow his suit and go down to the quantum size, and we could see or feel the electrons moving and slow down the movement of these electrons, or the energy at least, not the movement of the electrons, but the energy. We'd energize the power source, energy starts flowing. Electrons is flowing. Not quite at the speed of light, but almost close enough, right? So goes by like this. So yes, resistor does come first, diode comes next in the first circuit. And in the second circuit, diode comes first, resistor comes next. But by the time we humans, even we blink, we are already looking at the result, right? Because it takes place, I want to say, I don't know, picoseconds, femtoseconds, 10 raised to minus 15, 10 raised to minus 12, that quick, right? If you just think about what is happening right now, I have this wireless microphone that I'm speaking from. It's converting sound waves into electrical signals. Those electrical signals are again being remixed, modulated, and sent wirelessly into the receiver. That receiver is converting those wireless signals into a further electrical signal. That signal is again electrically processed, and via a software application, it's being sent out on the internet. And the internet, well, it could be wireless internet, but right now the internet is hardwired into the wall. But anyone anywhere in the world, 8,000, 10,000 miles away, could be listening to this right now live. And at their end, it's the same thing. It's everything is being reproduced. And there would not be a delay of more than, I want to say, half a second or 1 second, 10,000 miles away. So that's how incredible it is, right? It's really fast. So yes, as I was saying, if you were to look at it at the very, 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 very slow speed, meaning just one electron moving at a time, then yes, you would have resistor voltage would be different, diode voltage would be different, but we are looking at cumulative effect. So absolutely no difference between the two. The difference between the two examples is from the fact that the output is taken from two different locations. So if you take the output across the resistor in either circuit, it is the half-wave rectifier. If you take the output across the diode, it is the clipper or limiter circuit. Right? It's either the clipper or the limiter circuit. That's all it is. And to make it even more, I want to say confusing, but all of these circuits can be, sometimes are used synonymously. So rectifier circuits are also clipping circuits, right? Because the negative half cycle is being clipped. So negative half cycle, we don't obtain any output, so it's clipped. So a rectifying circuit is also a clipping circuit, and a clipping circuit could also be called a rectifying circuit. So they can be used synonymously. Okay. All right. Let's go to the next slide. And that would be 17. On the first page of this one is simply a summary. This is something that we already covered. This should help you in understanding how to approach problems with these kind of diodes. Okay. This is basically a continuation of the example that I just made. Now that I think about it, that explanation probably should belong on this page. But this circuit is this one, where resistor comes first, diode comes next, and then this circuit is the one we have diodes, and then the output is taken across the resistor. And as I made the clarifying point, the circuits are exactly the same. The only difference is where we are taking the output. If we connect the diode in parallel, not in series with the voltage source, then it's a different circuit. Okay, then it's different. But as far as series connections go, exactly the same circuit, no difference. Let's see. So from here, we are going to look at digital logic circuits. You all have studied digital logic in 133. So you're familiar with the binary number system, logic gates, and or not NAND, NOR, XOR. And so for the next few slides, we're going to discuss how we can implement digital logic circuits using diodes and resistors. And the first up in there is the concept of pull up and pull down resistors. Okay, pull up and pull down resistors. Pull up and pull down comes from the fact that we are going to but connect our circuits or our outputs to either a high voltage level or a low voltage level. So up, as the name indicates, is going to pull it up towards plus 5 volts or plus 10 volts. And down means it's pulling it towards 0 volts or a negative level, exactly as the name suggests. So up indicates positive, and down indicates 0 volts or negative. So digital logic circuits typically go between 0 and 5 volts. Okay, 0 and 5 volts. All right. So the concept here is simple. We have a source. Let's say the source is 5 volts. And 5 volts is considered logic high or 1. And 0 volts or ground is considered logic low or 0, binary number system. Right? So now we have a voltage control switch, or let's say any kind of switch for that matter. We have a switch, right? That switching device. We are applying an input to it. That input causes the switch to either close or open. Okay, that input causes the switch to close or open. So in the first one, right here, where the output is connected above the switch and the switch is connected to ground, if it's open, let's see. If it's open, it is going to connect the output to plus 5 volts via that resistor. And so we say this switch is going to give us a logic 1 or high. If the switch closes, then it connects to ground, gives us logic 0 or low. Does that make sense? Right? The same thing happens on the other side. On the other side, we are using a pull down resistor. So the output is connected through a resistor to ground. And so when the switch is open, we obtain a logic 0 or low. The switch is closed, the output gets connected to 5 volt. And so we obtain a high logic 1. Okay. All right, let's take a pause. Let me know if you have any questions. So on the second circuit, the output is permanently connected to the resistor to ground. So if the switch is open, the 5 volt supply is not connected for this case. And so the output is logic 0 because it's going towards ground. And then when the switch is closed, the output is connected to the plus 5 volt line. And so then if it's connected to plus 5 volts, it's logic high. Yeah. All right. Any other questions? Yes. Oh, the input could be anything. So a question being asked is, what is the input? Well, actually, you know what? Let's go to the next example. This one. And keeps doing this. Okay. So the input could be anything. It could be well, if it's a voltage control source, there could be a voltage that we're applying, right? If it's a current control switch, it could be a current that we're applying. So it could be anything. Doesn't really matter what it is. All it means is that the input is activating the switch. That's all. Now, what kind of input depends on what kind of switch it is, right? So again, the question being asked was, what is the input waveform and what form does it take, right? And so again, that depends on the switch that is being used. Speaking of which, if we have a voltage control switch like the CD4066, like this one, which is a voltage control switch, so we apply a certain voltage to the inputs, pin numbers 13, 12, 6, 5, right? 5, 6, 12, and 13 are the inputs. So we apply a voltage range to the inputs and the switches will activate. A higher voltage, switch will turn on, lower voltage, it turns off. Okay. Operating range is between 3 volts and 18 volts. And the switch turns on like an ideal switch. If you recall from a few slides ago, when the switch is on, the resistance for an on switch is 0 ohms. If it's off, it's infinite, right? Here, it's a voltage control switch implemented using semiconductors. So when it turns on, it does not have low resistance. The resistance is specified right here. If you use VDD 5 volts for that system, the on resistance is between 470, so about 500 to 1,000 ohms. That's huge. 1 kilo ohm is a huge resistance, right? And then if you use VDD as 10 volts, is between 200 and 400. That's still significant. So it depends on our application of what we want. The switch itself will consume some voltage across its terminals, which is just a byproduct of what it is. So in this case, that switch CD4066, it requires application of some voltage. You apply a voltage to it, like a high logic high, and the switch turns on. And if you apply logic 0, switch turns off. Okay. And the voltage or the current can come from any physical quantity. It could come from pressure. It could come from temperature. So as an example, we have thermostats we have a thermostat here. It doesn't work, but the logic behind the thermostat is there's a thermal sensor in there. It senses the temperature. It changes a physical quantity, changes its value, and it translated into electrical signal. So depending on the system, if the temperature increases, the voltage increases. If the temperature decreases, the voltage decreases. So once it crosses a certain threshold, it sends a electrical signal, switch closes, and your heater or cooling system turns on, right? And that's an example. This is a real life example of how we can use that. But here, let's talk about logic inverters in the few minutes we have left. So everybody is familiar with an inverter, right? You've done NOT gates in 133. All right, so pull up resistor going all the way to 10 volts, voltage control switch. A is the input, out is the output. So VA and V out. When VA is 0 volts, meaning logic 0, this is the circuit result, right? You're applying 0 volts to the switch turns off, meaning it's off, and your output is connected to 10 volts. So you obtain a high when the input is low. Your output is now the inverted or inversion of the applied input. Okay. And the same thing happens when you apply logic high. When you apply logic high, switch turns on. Now your output is connected directly to ground. However, we have to take the resistance, the on resistance of that switch into account. Okay. When the switch is off, it pulls up to plus 10 volts. When the switch is on, it pulls it down to ground. That's what's happening. Okay. And the on resistance causes a small voltage drop across itself. So 0.476 volts. And the reason on resistance is important is, let's say, if R on is approximately equal to 4,000 ohms, then V out will be approximately, or not approximately, V out would be greater than 3 volts. It completely changes our output. Okay. So that's why the on resistance of these devices matter. Okay. All right, questions. We have just enough time to answer some questions. Anyone? All good. Yeah. This is absolutely correct. The question being asked is, where does R on come from? Right? R on is just basically on, you know, how the switch is designed and what material is made from. Absolutely. It's usually made from semiconductor devices. So real life MOSFETs that we use, they have pretty good, like, you know, low values of resistance. Yeah, almost none. Okay, we'll end class here today. I'll see you all on Monday for the quiz. And then quiz will be based on the material we covered this week. And I will post the last 2-3 homework assignments for this month. Shortly. Be one pretty much due every week. Okay, have a good weekend, and I will see you all on Monday.